Hello and welcome back to our studies in physics. You'll recall several lectures ago we talked about the fact that Newton in his lifetime developed all the laws necessary for us to be able to quantify the motion of all objects in the entire universe that we can see with these detectors built into our head. 4 laws that he developed. The first 3 we've already been looking at, and I've just summarized them here. The first law is known as the law of inertia. It suggests that when an object is in motion or a state of constant velocity, that it will remain in that state of constant velocity in the absence of unbalanced forces. In other words, we add up all of the forces vectorially, we end up with 0. That means the object experiences a state of constant velocity or a state of equilibrium. Remember, those two mean the same thing. Constant velocity and equilibrium are synonymous. His second law now tells us how objects will behave when we sum up all the forces acting on an object and we don't get 0. So notice that if we sum up all the forces acting on the object and the numerator is 0, then there is no acceleration for the object, and we're up here in the first law where the object is in a state of constant velocity. But if instead we sum up all of the forces vectorially and we do not get 0, then that unbalanced force, whatever we end up with when we add them all up, divided by the object's mass, is going to give us the acceleration, both the magnitude and direction, for an object. His third law tells us that forces come in pairs. You can't have an isolated force. There is no existence of an isolated force. And to find the third law pair, you just simply switch the nouns for your description of the force and the direction to identify that third law pair. So for example, I push down on the floor pushes up on me. So I describe the force that I'm interested in finding the third law pair, and then I just take the 2 nouns in that sentence that describes that force, switch them, and then switch the direction, and that provides me the third law pair. The last law that Newton developed to, again, quantify everything that we can see in the universe with these eyes is the universal law of gravitation, and that's the subject of this video. So if we have 2 objects that have some mass, so let's say this is going to be our object that has mass m1, and this is another object that has mass m2, and they are separated, their centers are separated by a distance r. Please notice that r is not being used as radius here. In other words, we're not defining the radius of either of these objects as r. We're defining the distance between these 2 objects as r. So r is used as a radius in some parts of physics and as a distance in other parts of physics. And we need to understand the equation very well to know which we are to use in that particular equation. So here we have 2 objects. They have masses m1 and m2. Their centers of mass are separated by a distance r. What Newton discovered in his universal law of gravitation is that all mass pulls on all other mass. So force of gravity is attractive. Always. In other words, I'm gravitationally attracted to you. I'm gravitationally attracted to this glass that I'm writing on. I'm gravitationally attracted to this pen. I'm gravitationally attracted to every single thing that has mass, including things on the other side of the universe, and they are gravitationally attracted to me. So all mass is pulling on all other mass. That is what Newton's universal law of gravitation tells us, and that allows us to define the direction part for the force of gravity from one object on the other. Objects always pull other objects toward them, so along that line that connects them will give us the direction of the force. So for example, mass 2 feels a force from mass 1. Mass 1 is pulling mass 2 toward it, so there's going to be a force felt on mass 2 that we can describe as the force on mass 2 by mass 1. In addition, mass 1 feels a force exerted by mass 2. Mass 2 is pulling mass 1 toward mass 2, and so there is a force on mass 1 that is the force on 1 by 2. Notice that these two forces describe a Newton's third law pair. All we do is switch the nouns and the direction, and we can define the other force. So just for example, looking at this force, this is the force on 1 by 2, and it's pointing to the right. This is the force on 2 by 1, and it's pointing to the left. So that clearly defines a Newton's third law pair as well. So these give me the directions of the two forces. What about how large they are? Well, the magnitude part of the forces exerted gravitationally on one mass by another is going to be equal to a constant. This is a universal constant, big G, of which we'll define in just a moment. Product of the masses involved divided by the distance between their centers of mass squared. So notice again, R is equal to the distance between objects' center of mass. Very distinct definition, as all quantities are in physics, okay? Understanding the definition is 90% of the physics. So you've really got to get a good handle on that. R is the distance between the two objects' center of mass. So this gives us the magnitude part of the universal law of gravitation. The direction part comes from the fact that the force of gravity is always attractive. Okay, so objects always pull directly on another object. Let's go ahead and define big G. Big G is known as the universal gravitational constant, and of course it's involved in all gravitational interactions. Big G is equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So there is big G. If I'm interested in calculating the force of gravity that I exert on this pen, for example, then I would measure the distance from the center of the pen to my center. That would be the R that I plug in. I would find the mass of this pen. I would then find my mass. I would plug in both of those masses in units of kilograms, and then using our definition for the numerical value of G, I would put all of these numbers into my calculator, and that would tell me how large the force of gravity is that I'm pulling on the pen with, and that the pen is pulling back on me with. The direction, of course, comes from the fact that it's attractive, so I'm pulling directly toward the pen, so the pen feels a force that's along the line that connects me to the pen directed toward me. I feel a force from the pen. I'm being pulled by the pen. Again, the force is directed along the line that connects me to the pen and would be pointing to the pen. So that describes Newton's universal law of gravitation. And in the next video, what we're going to do is talk about why it is that even though I'm being gravitationally attracted by everything in this room, and everything in this room is much, much closer to me than the center of the Earth, why is it that I do not pull these objects toward me or get pulled toward them? Why is it that instead the gravitational interactions being dictated by the Earth? So we're going to look at that next time.